So the word logarithm. So the logarithm of a number, what is it? To explain that, let's start with an exponential expression, as always. Let's say you have 2 to the third equals 8. Okay, so we have base, power, and a value. So basically, log, just like we did with the radical. So log is just another way to go back to go back from here back to this back to the base here. So we can say first we're going to need the log. So to change, this is an exponential expression. To change this back to a log expression, so we're going to need the word log, short for logarithm. I'm going to write log, and each log must have a base. Okay, so the base here in this expression is also the base of this log, usually a small number here, down here by g. Okay, so let's say log base 2 of 8 is 3. So log of 8, so log of 8 is 3. Again, we're just going back. The log basically allows us to go back from the value back to the base. So log of this number is 3. And the base in this power is also the base of the log. That's basically what a log is. It's just an inverse way from the exponential expression back to the base here, back to this number, the log of the base. Kind of like we said, like we did with the radicals. So the radicals we saw the other day is that if you have, let's say, 3 to the second is 9, we take the radical of this number, right? And again, the exponent here is the index is 3. So we can go back and forth between exponents and radicals. Same thing with logs. So that's what a log function is. That's basically we can switch back and forth between any logs simply by doing this. Okay, and let's do another example here. Well, if you take any example, basically any exponential expression, you can turn it into some log. Let's say 3 to the 4th is 81. Again, we can switch this to, so the question will say, express this or switch this into logarithmic form. So first thing you do, you're going to need the log. Then, what is the base of that log?
Log 8.
3.
Oh.
The base is the base, that's right, small number here.
Oh, you mean, yeah. Okay.
Okay, so log of what? Log of 81 equals?
4.
4. So it's that simple, okay? So log, we'll read this as log base 3 of 81 is 4. So log base 3 of 81 is 4. Again, log of this number equals this number, and the base stays as the base here.
When they give us a problem like this, they would be asking us to find any one of these?
Yes, it'll either give you this or this and ask you to switch back and forth between them. That's one of the questions. Okay. And there are other things that we can do with the logs. We're going to see those in a moment. You may also see something like 25 to the power 1/2. 25 to the power 1/2. 1/2 is this, power 1/2 is the same as the square root. Power 1/2 is the same as the square root. What's 25 to the power 1/2?
5.
Just 5. Okay, so whenever you see power 1/2, it's not square, it's square root. So 25 is 12. Same thing with the cube. What is, for example, 8 to the power 1/3?
2.
That's right. So when you see the power 1/3, it just means the cube. Okay, the cube. So the opposite of the third power is the cube. So this is the same as writing the radical with index 3. So this is 2. And these exponents, we can write them as logs. So log of, for this one, log base.
25.
Log base 25. The base here is
2. 2.
no,
25.
we're not changing the numbers here. So the base here is 25. It remains the base. The log of what?
5.
Okay, equals
1/2.
Teacher,
Or-
but how do you know that 25 to the half power? How do you do that?
It's the same thing like when you have the radical, and remember the power, the index is 2, and then underneath the radical, the power is 1. So you take the 1 and you put it over the 2. That's how you end up with that.
That's right. So that's exactly as she explained it. Okay, so that's log. Let's do this one. So log of what base? Let's do this one here. So switch this exponential expression to a log.
Log of base 8
Mm-hmm.
2
Log of 2 base 8 is
1/3.
1/3. Okay, and this is something we can also do with the calculator. There's a button in the calculator called log. Okay, so we can do that. You enter the base, you enter the value or the number, and then you get the value. And let's see. Now let's see how to solve some logarithmic equations. So equations with logs, you may see them. We'll see how to solve them and find basically the log. For example, log of x of something is something. Find the value. To do that, let's first solve some logs without a calculator. Now that we know the rules here, especially exponential rule and the log rule, we can actually solve logs. I'll give you some logs and you'll see that it's very easy to solve. For example, so if you look at it this way, or if you look at it here, so log, basically 2 to the third is 8, 2 to the third is 8, or the base here, 2 to the third is 8.
Mm-hmm.
If you have this, if you don't know this or this, you can figure out what's missing. So 2 to this power is this. Let's say you had x here. Let's say we didn't know what the number was. So basically just take 2, raise it to the third, and it gives you this number. 2 to the third is 8. Same thing here, 2 to the third is 8. Let's say this one was x. So if I gave you just this part, I said, what's log base 2? Gave you an equation like this. It asked you what x is. You say 2 to the third, and you put the number. So it's pretty simple to find the numbers here. Let me give you some examples. Let's say we don't know this log here, base 4. So log base 2 of a number that we don't know is 4. What's that number?
The 16.
32.
Right? 16. Very simple. Just take 2, raise it to this power, and you get x. So the first thing you want to do, you don't have to do it in your head. You can basically we change this log equation, just like here, into an exponential equation. So we're going to say 2 to the power 4 is x. Is x actually not is x. So 2 to the power 4 is x. Because 2 to the 4 is x, as we said earlier, so we change this back into a log. You take log of this number to this space equals 4. So we change the log into an exponential expression, and then we solve it. So there is a rule here that we need to know. If you have a to the power, let's say, x to the power a equals x to the power b. What does this mean in terms of the values of A and B?
They're interchangeable.
Which means
They're the same.
mathematical, well, they're the same. That's right, they're equal. So if you have the same base here and some powers that you don't know, so those powers gotta be the same. So this implies that A equals B. Okay, there's no other way. So if this base is the same, the powers here must be the same. So that's pretty much how, so to solve log equations, we turn them into exponential equations. And to solve exponential equations, basically, we try to make two sides with the same base. Once we make two sides with the same base, we just ignore those bases and we say these must be the same. If these two are equal, the powers must be equal. So let's try to do that. Let's try to do that in this example. Or maybe another one. Let's do another one. Let me see if I can find a better example to explain this.
Would, maybe I'm crazy, but 2 to the 4th would equal 4 to the 2nd? I mean, if going by that rule.
2 to the 4th would be equal to
4 to the 2nd, because isn't 2 to the 4th 16 and 4 to the 2nd is 16?
That's right. So the x here, yeah, x is 16. That's what we said earlier. Trying to put this into an equation like this to show you exactly why it's that. But we can actually, okay, so we can say that x is 16. So this one is pretty straightforward, okay? Straightforward, as we said, 2 to the 4th is x. So again, this we can do without a calculator. If I give you this, you can figure it out without a calculator. Let's see now if we have, if the x is here. Okay, so if we're missing this, we can do this to this power is this. If you're missing the x here, that's where this actually is useful. Let's do, so log base, maybe some power, different base here. Let's say, okay, that's probably another simple one to figure out without the equation. What is x equal to?
27.
Okay, so let's say we have this equation. You don't know what the x is. Let's try to turn it into an exponential expression or equation and then solve it. So what is the exponential equation here?
Base is 2.
Just give me not the answer, just turn this
3
into,
to the 9th power.
not to
No.
the power.
It's 3 to the x power equals 9.
3 to the x is 9, that's right. So now we're gonna try to make this look like this, meaning we're gonna try to make them have the same base. Once we make the bases the same, the powers will be equal. So we have a base of 3 here. Can we write this as something with 3, with base 3 to
3 times 3.
as a
Will we factor it?
no, just want to rewrite this as something with base 3. What would
3
be
squared.
3 squared? As you can see now, that looks like this. The bases are equal. That means
That x is 2.
that's right. X must be equal to 2 because the base is the same. So x must be equal to 2. That's the solution here. Or we could have done it the same way as this. You could say 3 to a power is 9. 3 to a power is 9. That power must be 2. But this is the formal way. The numbers are not always convenient here. It could be some, I don't know, fractions here or decimals. So it's not always easy to see or do quickly in your head. But when you have an equation, when you turn it into an equation, you basically can turn it into an exponential equation and then solve that exponential equation. And checking it is should be pretty simple. So we can do, so 3, 9, we're going to plug the x, which is 2, and see if this works, if this checks. So again, this is a log expression. Let's turn it into let's double check this by turning it into the exponential expression. A is 3 to the second equal to 9. We say, yes, 3 to the second is 9, and that's 9. Or you can also use a calculator to check here. So log base 3 of 9 equals 2. Okay, so these are pretty simple log equations. Sometimes you may see, instead of just x here, we may have x plus 2 or plus 3. Same thing here. Instead of just x, you may have a whole expression inside the log. But the key thing here is to change that into an exponential expression, exponential equation, and then turn that equation into, and then basically try to make the same base on both sides. So let's see.
If you had an x plus 1, would you raise everything to the power or only x?
That's what we're going to see next, right? Now we're going to do a couple of examples like that. And let me see here. Okay, if you don't have any other problems here, let me make up some. Anyway, so let's say some base here. Could be any base, let's say 2. And maybe 4 here. Maybe some x plus 1, for example. Some x plus 1 here. Okay, find x. Same thing again, whenever you have logs, first you want to do is turn them to exponents. Exponents solve a lot of issues, just like we saw with the radicals. Whenever we see radicals, we might not be as comfortable as exponents. First thing you want to do, change them to exponents, and exponents are easy to deal with. We have a bunch of exponents power that we saw before, and we apply those. So,
Teacher, does it set final there?
find x.
Find x.
Oh, fine.
What is, okay, let's turn this into an exponential expression.
2 to the x plus 1 equals 4.
That's right. Very good. So that's first step.
X is 1.
X is 1. How do you know? We don't know yet.
Because, well, just looking at it, I would surmise that x is 1.
So before we can conclude that, we have to have the same base here. We're going to try to make 2 bases here on both sides, and then we're going to take, like we said here, once we make 2 bases here that are the same, we can take the powers by themselves in an equation. Okay, so we have power base 2 here. Let's rewrite 4 as
2 squared.
That's right, 2 squared. Now that we have the same base, we can basically just ignore that base. The equation turns into, the bases are equal. That's right. And now, simply subtract 1 from the sides. And
be minus 1.
X is 1.
X is 1.
So what you said, Carrie, you said 1, right?
Mm-hmm.
Okay, that's good. And that's pretty much how you solve logs. Okay, nothing too complex about them. They may look fancy a little bit, but they're just basically exponential equations. That's some.
You just have to figure out how to write the equation. Once
right.
you do that, then
Important part, yeah, converting the equation into a log, into an exponential equation. And once you do that, along with the rules of exponents, we can easily solve the exponential equation.
So is there any way that you would get, you wouldn't get the base? They would give you like what it equals to, but not, and the index, but not the base?
It is possible.
Yes. Log?
It is possible. Let's say you mean like here, give you the x's here instead of here?
Yeah, so the x would be where the 2 is instead of being on the other side.
That's unlikely.
Okay.
That's unlikely. I haven't seen an example like that. But if you do, let's say if you assume you have x here, then it would be just a regular equation. It would be just an x here, and it would be either a quadratic or a cubic equation, so it wouldn't be that bad. So you could have something like this. So log, let's say, I can do that. Something simple you can do yourself quickly. Okay, so what do you think the x is?
5.
5. Okay, because this to this power must be equal to 25. If you want to convert it, first you can say x to the second. X to the second is 25, and that's a simple quadratic equation, like I said. So x is 20. I mean 5.
Yeah.
Okay, so convert your equation, the x, whatever the x is, you can easily convert that. You can easily find the x.
So you wouldn't turn it into 5. Well, from how you had it before, you wouldn't make it 5 squared, which would then let you know that x is 5 because the bases have to be the same.
The base, yeah, you could do that, yeah. If you do here, the base would be basically the inverse of this. If you have the same power here, the base is, or if you have the same bases, the power must be equal. So you can write this as x to the second, and here something with power 2 here would be 2. And we have 5 here. So if the powers are the same, the x's or the bases must be the same. Okay, so let's do another.
Do you know that that one is 5 because you took the root, because the exponent turns into a root?
Pretty much, yes. Or you can think of it this way. This to this power must be equal to this.
Okay.
Okay,
Upside
so
down triangle.
solve based on the very first example we did here. So we can switch back and forth between logs and exponents. Let me see if we can do some more complex examples here. I should have a few here. All right, so here's this one. Basically, since when we turn logs into exponents, we solve them. So basically, we can have something like this. Basically, we turn logs into exponential expressions. This is one of the examples you may see. So now, based on what we've done before, okay, we want to solve this equation for x. What do you think we need to do first? These are, by the way, what we call exponential equations.
Have the bases be the same?
Exactly.
X is 1.
Not sure.
X is 1.
Okay, exponential equation. So when you see this again, think about the rule here. Since we have base 4 here, let's make base 4 out of this. Okay, so this 4 now stays the same. What is 16 as something with base 4?
4.
4 to the second. So what we're going to do is we're going to turn this 16 into 4 to the second. So it would be 4 to the second.
To the second, to the x.
That's right, but we still have that power there, x plus 2. All we did was change the 16 into this. Now, with the exponent rules, if you have x to the power a to a power b, what do we do with the powers again?
Multiply.
Multiply them, a times b. So we're going to take these two and multiply them. Kind of move the 2 out, and we're going to have the 4 by itself. Here we have 4 by itself, it will be 3x minus 3. This one here, it's going to be 4, and we're going to times.
4 to the 2x plus 4.
That's right, it will be plus 2. Now, as you can see, we have the same base, okay? So the powers, again, if the bases are the same, the powers must be the same.
Do you recommend to, how do you say, to do the 2 times 2x plus 2, or just leave it like that?
We can do it afterwards now that we have the same base. So the equation turns into what?
3x minus 1 equals 2 times x plus 2.
That's right. Now that we have the base, which is the same, we can ignore it. The powers must be the same. So 3x minus 1 is 2x plus 2. And the rest is pretty simple. We just solve this first degree equation. If you move this over, it becomes x and 5. And you can check for yourself. You'll see that it's pretty simple. If you plug the 5 here or here, those should be equal.
Oh.
Okay, so that's another type of equations. So we saw first degree, we saw second degree, logarithmic equations, rational equations, radical equations. Today,
How does that? Wait a minute.
another
Something
type of equations. So log equations and exponential equations. So again, log equations, turn them into exponential equations before you solve them. Sometimes the solution can be easy, like
15 minus
like
1.
here. You can just say, if it's this simple, you can just write the solution right away. 3 to a power is 9, that power must be 2. Or if you can't see it, you can always do this. Let's see in the case where you may end up with different equation than that. Let's see. By the way, so these are logs, like I said, logs and exponential equations basically inverses to each other. So one takes you back to the other. So you go from exponents to logs, we can go back. Even their graphs kind of look identical, actually. Not identical, but symmetric. So let's say this is the graph of an exponential function. And the other one is just the inverse of it. The other graph looks like this. If you graph them the same way we did before, I didn't want to do that again. When you plug x's and find y's, you'll see that their graph is symmetric, or basically the one graph is the inverse of the other graph across the y-axis. So usually this is the exponential expression, exponential equations, or functions. They go like this. Log functions are inverses of them, so they go like that. Just a little step there, a lot of important information about logs and exponents. And to graph any function, any type of function as we saw before, again, just take values of x, plug them into the function, find y's, plot your points, and you'll see the shape of the graph. And from the graph, you can read a lot of information. For example, the domain, the range, the intercepts, and any other information you may need. That's basically, let's do, so we can do a couple more problems here. Okay, let's make up some problems. Let's say we have 5 to the power 2x plus 1, and we have 25 to the power 3x minus 4. Okay, so that's again an exponential equation, which you may get from a log. So if you ever have a log equation, it turns out to be this way. So basically, knowing how to solve exponential equations is basically solving logarithmic equations. All right, what is the first step again here?
Get the same base.
Get the same base. Okay, so look at these bases. We have 5 here. We're going to try to make 5 out of this. So it would be 5 to the power.
2.
That's right, to the power 2. Let's write it first inside here. And this stays the same, 3x minus 4. Now we can move these two outside or multiply so we can have 5s by themselves. So we can say 2x plus 1, 5, 2x, 3x minus 4. Okay, once you make these bases the same, So ignore the 5s. So you're going to have 2x plus 1 equals this what? 6x minus 8. If you move this over, it becomes negative 4x.
We multiply. How do
Mhm.
you get 6?
Yeah.
Because it's 2 times 3.
Times 3.
Okay.
Okay, so you move this over, you subtract them, you move this here, it becomes negative 9. Divide by your negative 4, so it would be 9 over 4. Okay, and that's pretty much it. That's the solution. Again, you can play around with it, plug the numbers in and simplify. Okay, so that's basically logarithmic properties. Or this is basically, you could say, log and exponential equations. That's pretty much.
I have a weird
So
question.
far, now we're going to see the properties of logs. Yeah, go ahead.
Okay, so you see how we just got x equals 9 over 4?
Bottom.
Would that then turn into, like, let's say that you wanted to use the radical symbol, you would put the 5 under the symbol, the 4, it would be like 5 to the 4th, radical 5 to the 4th, and the index would be 9? Or would it translate that way?
You want to turn this into a radical?
Well, the initial base would be the radicand, and then it would be raised to the 4th power. The index would be 9. That's what I'm asking.
So this is, you want to, so basically we have an exponential expression. You want to turn it into a radical, right?
Yeah, so I'm asking if the x that we ended up with,
So,
x equals, yeah, I'm trying to figure out how would we get that back, like, into the radical symbol if we needed to.
this usually would have to have a value here, let's say some value y. Now we can turn this into a radical of y. So you would have to put this whole thing inside here.
Okay.
And I don't think we need to do that. There's no need for that. So that's a completely different topic. This is just solving. As for radicals, so you take y and the index. What's the index of the radical? If you want to turn this into, the index will be?
2.
No, we don't have a number here. So just work with the numbers we have. So radical of y, what index? The power becomes index is a. So if you had an exponential expression, you can still do that with here, but I don't think it's something that we need to do.
But it's not something we're gonna have on the test, right?
No, we'll not be mixing up logs and radicals. They're completely different, but it'd be just one thing. You will have to do one thing at a time, not multiple things.
Okay.
Okay. Let's see what else. That's pretty much it, I believe. There's plenty of examples in the homework. I believe they should be similar to this. So a lot of solving. If you see any graphing in the homework, it's pretty simple. Okay, just plug the x, plug a bunch of x's, find the y's, and if you need to find the graph, you can find, the domain and range from the graph, you can do that.
Can you give an example of that, Professor?
Say that again?
Can you give an example of that? We get the graph and then we have to figure it out.
I don't think you'll see them in the homework, just in case you see them, just in case. If you see them, just go back to the same thing as we did before, but I don't think you're going to see them. Let's talk about logs a little more. We have a bunch of rules for the logs. Let's first, let me see if we have a lot of time. We could probably go over them. Here we have about 5 rules of exponents, of logs. Let's actually see if we can do them also or not. Let me do those next time because we have a bunch of them. Let's talk a little bit about, as I mentioned before, inverse functions. Briefly explain inverse functions because logs and exponents are inverses of each other. Okay, so basically, when you have a function, as we saw before, let's say you have a, b, and b and c, and you have some values. You have -1, 0, 5, for example. This is a relation. Is this relation a function?
Yes.
Because one from here has exactly one value, as we saw before. Each one has a value. Not only that, each one has exactly one value. It could still be like this, and it would still be fine. No, not this way. It could be this way, and it'll still be a function, as we saw before. It could still be this way. One for two values or more here may share the same value from the other side, and it's still a function. For example, two students having the same age here. But what's not good is this way. If you have one element from here with two values or more from the other side, so that's not a function. So for this one here, it's exactly 1-to-1, 1-to-1, 1-to-1. In that case, if you have a function that's exactly 1-to-1, not even having this is still a function like this, but it's not exactly 1-to-1 because this element here has basically two corresponding values from the same group, first group. It's still a function, but it's not exactly 1-to-1. If a function is 1-to-1, then you can find an inverse to it. What this means is, let's say this is the function f, and whatever x might be. So if you plug, what is f of a? F of a is negative.
-1.
That's right. F of b is 0, f of c is 5, and so on. So basically use f of x to go from this side to this side. There's actually a function that allows us to go back from this to this. Another function based on this that allows us to go from here to here. Since this one is 1-to-1, it must be 1-to-1 before you can find an inverse function. That function is what we call f, and there's a little symbol here, f inverse of x. This is not a power, it's just a symbol, it just means inverse.
But is it a -1?
Yes, but it's not a power, it's just a symbol for inverse. So again, to go from here to here, we use the function f. To go back, we have a function we call f inverse. What is f inverse of -1?
A.
That's right, it will take you back to a. F inverse of 0, just basically, let's say you're going from A to B, and you take in some road. So A to B, let's say that's the function f. To go back, you take x to y, actually here, say x to y. You can go back from here, taking another road that's inverse to the other road. Pretty much the same, let's say highway, one way, and then the other way. So that's what the inverse function is. For any function, you can, if it's 1-to-1, it must be 1-to-1. If it's not 1-to-1, you can't find the inverse because, for example,
Is that why 4 to the 14th is equal to 16 to the 7th? Would that be like considered 1-to-1?
14 to the
4 to the 14th power equals 16 to the 7th power. Is that that seems like to be the inverse?
maybe, not sure about it, but probably. But let me explain now another example here. So let's say you have first of all, is this a function?
Yes.
A function, but is it 1-to-1?
No.
Exactly, but it's not exactly 1-to-1 because each one has to have exactly one. This one looks like it has two from here. It's still a function, but not 1-to-1. And if it's not one-to-one, do not even try. There is no inverse. You can't go back, because if you want to go back, let's say you think the inverse is some function here. But if you plug 3, what do you want to get? Are you going to get A or are you going to get B? So it won't be consistent because it's not one-to-one. So this does not accept does not have an inverse function. Again, because it has to be consistent. If you plug 5, every time you get C. If you plug 0, you get B every time. For this one, if you plug 3, are you going to get A or B? We're not sure. So this is not a one-to-one. Therefore, there's no inverse to it. So you can easily see here whether a function is one-to-one. Literally, you have to have one line only between any two values. If not, it's not a one-to-one. Therefore, it doesn't have an inverse. What about from graphs? Let's see. This is what you do to figure out whether a function is one-to-one from a graph. So we do not, when we do the, let's talk about the functions first. Is this graph a function?
Yes.
Yes, so we do the vertical line test as we saw before. So if it meets once, it's a function.
But it's not an inverse.
Okay, if it meets the graph only once, it's a function. How about this one? Is this graph a function?
No.
It's not a function.
No.
3 times.
Three times.
You do the vertical line test to determine whether a graph is a function. But to determine whether a function is one-to-one, these are functions, but not necessarily one-to-one. So to determine whether a function is one-to-one, we do what we call the horizontal test. Okay, so horizontal test.
You said the vertical test is to see if it's a function or not. On the horizontal?
Yep, I'm writing it right now. Determine whether is one-to-one. Okay, this is still a function, but is it one-to-one? We do the vertical line test. I mean,
No.
horizontal line test. How many times?
Twice.
Twice. So is it one-to-one?
Nope.
Exactly.
No.
It is a function as we saw here, but it's not one-to-one. Can we find an inverse of it?
No.
No. So if it's not one-to-one, there's no inverse. Again, the vertical line test is to determine whether it's a function or not. The horizontal line test is to determine whether it's one-to-one. If it's not one-to-one, there's no inverse. So this is one of them. Here's another example. Let's say we have this graph. So basically, we have this graph.
पानीले एक गिलास मान्ता त यति छिटो तथा पकाइ सेलाउने भयो भनेको साह्रै
Quick question for you. If something is not a function, it's automatically not one-to-one also?
That's even like, yeah, so more than one reason not to be a function.
Mhm.
It has to be a function and one-to-one. So let's say this function here, which is a linear function, is it one-to-one?
Yes.
That's right. Anywhere you do the vertical line test. Anywhere you do the vertical line test, it will always meet once. So linear functions are inversible, or they accept inverse. So a function and one-to-one. That means it has an inverse. This is probably, oops, what happened here? It's probably one of the clearest examples of inverse functions. Therefore, it has an inverse. Okay, so speaking of these linear functions, I have to draw one here. So So they're probably the easiest to find linear, to find inverses for. So let's actually find a natural function and actually use it to go back from the domain to the from the range back to the domain. Okay, so finding. Okay, so as we saw here, it's a linear function. So from now on, you can say any linear function is basically inversible, if that's a word. So because we know it's a straight line, and anywhere you draw that horizontal line, first of all, we know it's a function. Okay, we already know
Would
that.
only linear ones be inversible? What about the one that's like a straight line and then it curves and then it's a straight line? Okay.
Depends. So do your tests. So both the vertical and the horizontal line test should meet only once. That's basically what a one-to-one function is. If not, then it's not, it doesn't have an inverse. So we know for a fact, as we studied before, that linear functions, functions are not one-to-one. We just learned one-to-one today. First degree functions are linear and they only meet once, as you can see here. And they're also one-to-one because horizontally they only meet once. So that basically, we have a function that goes from the domain to the range, and we can definitely find a function that takes us back from the range to the domain. Just test a few values here. What is f of 0? If you plug 0 here, you get 4. What is f of -1? If you plug -1 here, -2 will be 2. F of -2, it's actually already here. F of -3. What is f of -3?
-2.
Right? -2. Okay, so no problem. So we have f. We can go back from here to here. We use f. Now let's find our way back. So we need something to plug 4 into to get 0 and plug 2 into to get -2 and so on. So that's the important part in all this. So first you want to, as we saw before, f of x is y, right? F of x, you get some y. So we're going to replace the f of x here with y, okay? Again, because f of x is always equals to some y. So instead of writing f of x here, we're just going to substitute it with y. So it'll be y equals 2x plus 4. Now, what we're going to do is we're going to switch. Let me write those steps here. Replace. F of x with y. Second step, you want to switch or swap x and y.
And this is to find the inverse function.
Mm-hmm. That's right. So swap x and y. Swap x and y or x with y. Okay, basically instead of whenever you see a y, turn it into an x, and if you see an x, turn it into a y. So y here turns into an x. And this x.
It says swap x and y.
Mm-hmm. Swap x and y, x with y. So anywhere in the equation, wherever you see y turn into an x, whenever you see x turn into a y. And the third step is to solve this for y. Solve this for y. And once you do that, you will have your inverse function. And we're going to test it and see if it in fact works. Solve for y. Okay, so that's an equation. Let's get the y by itself on one side. So what's the first thing we do? We want to get this by itself.
Add
X
4.
minus 4 over 2.
What's that?
minus 4.
Subtract 4, subtract 4, end up with 2y. These cancel out, x minus 4. What else to get the y?
Over 2.
Right, divide by 2, pretty much divide everything else by 2. So now we can say the y equals x over 2 minus 2. So that's basically our inverse function. So y is x over 2 minus 2. Now we can switch back, we can switch this back to, so once you get the y by itself, that's basically your inverse function. So this would be f inverse. Again, this is not a power, it's just a symbol, which means the inverse. Okay, so that's the inverse here. So 3 simple steps. You can turn any, you can find the inverse of a function if it actually it's a one-to-one function.
Teacher, so for example, if you were to get fx, right, and then you would be given all the values of y, you would have to find the inverse, so then to find all the values of x.
Yeah, well, usually depending on the function or the question will tell you what to do, or to find this, or find the inverse, or test it. So this is our inverse function. So to go back, we need f inverse. So if everything is correct, if our math is correct, if we plug this, we should get back to this, this, and that. Okay, so let's try that. Hypothetically speaking, f inverse of 4 should be, according to this, f inverse of 4 should be
0.
0. So let's see if that works. Okay, because according to this, if this is f inverse should take us back exactly where we were. That's why the function must be one-to-one. If it's not one-to-one, it doesn't have any inverse. All right, so let's plug. So inverse of 4 means we're going to plug the 4 here. So 4 over 2 minus 2. 4 over 2, that's 2 minus 2. It's 0. As you can see, it works. And likewise for the rest of them, if you plug this, you get back to that. Okay, so that's basically how inverse functions work. So again, check first if it's one-to-one. If it's one-to-one, then find your inverse. These are the main steps. It might be a little more complex than this sometimes, but again, just make sure you follow these steps. The rest is just arithmetics and solving.
Okay, so you
Professor.
solve the equation for y,
Mhm.
and then to check it, you go back to the original equation and plug in the values.
Right. So
Of
if you don't have a table already, just take one value, find f of x with that value, and take that y and plug it in the inverse and see if you get back to this. If you don't have a table, feel free to plug in a value here. So if you go back and forth, you should be consistent, okay? Should be consistent and should be able to go back. You know, a lot of stuff nowadays, we need to go backwards, especially in the computer science field. Let's say, for example, you delete something and you knew what you want to recover it or reverse the action. So a lot of that stuff in the background is basically functions like these, much more complex functions that run in the background when you click and press and tap. A lot of this stuff, sometimes we need to go back where we were. Reverse an action or undo. Undo, if in Word, for example, you do something and you want to undo it, that's pretty much an inverse function. And trust me, it's a lot of math going on behind that simple action that you take simply by clicking something. So we should be able to backtrack and go back and forth between two actions.
Yes, sir.
Mm-hmm.
We will have an inverse functions in an exam.
What is it?
We will have in an exam inverse functions.
I don't, probably not. I don't see them in the review sheets for some reason. They haven't been there in a while, but you never know, maybe.
oh god.
Are
Okay,
they
thank you.
good, right? You want to see them? You want to see them in the exam?
No, we don't want to see that.
Is
We
that
don't
not
want to see any graphs either.
No, we don't want to see.
Not that, but it's not that.
easier than a lot of things, you know? It's easier than a lot of things.
Yeah, we don't want to see it, Professor.
We'll see. Okay, so anyways, I wanted you to learn that, to know it. If you
How
go,
many questions are going to be in the exam?
Hmm?
How many questions are going to be in the exam?
be 20, just like last time.
Oh Lord.
Oh, Lord.
Okay, so we saw basically
Professor, can you go back down a little bit to the last part of what you were writing?
So we saw log and exponential equations, which are pretty simple to solve. And we saw the inverse functions. Next class, we're going to talk about logs. We have a bunch of log properties, at least 5 of them. I wanted to allocate a whole class just for that because there's a lot of them properties and examples, so we want to do a whole class on them. They're not difficult, it's just a lot of stuff to learn, so we'll do that next class. Our final lecture will be next class, basically. Tuesday, Thursday, yeah. Any other questions, everybody? Did you have any questions for me in the beginning?
The finals is next week, Professor?
It is, yes.
Okay.
What day,
Next week,
Professor?
right, Professor?
Wait, you said the
next
final
week?
is next week?
It is, yes, Tuesday.
Okay.
Again,
You said Tuesday or Thursday?
posted the review sheet. I posted the date and details on Blackboard and sent you an announcement as well.
Okay.
Oh, man.
Professor, a quick question. Did you take attendance?
Not yet. I'll take it.
Okay.
No,
No, because I log in 10 minutes later, so that's what I'm asking you. I don't know.
Are there any other questions, everybody? And also don't forget to post something to the discussion board today, week 14.
Ugh.
Did anybody have questions in the beginning?
Yeah, I did.
Mhm.
I had a few. So my issue,
Mhm.
because it seems to be a recurring issue. So that I don't know. For some reason, I feel like it's something I'm supposed to know, but I just can't figure out why I keep getting stumped on this. When you have a variable
Okay.
underneath the radical,
Mhm.
so like let's say 3 times radical 72m squared minus 5 times radical 32m squared. For some reason, I don't know, it's like I'm getting messed up because I don't know if I'm supposed to be factoring out the m or what the heck is supposed to be going on with that.
Basically what you do is split them. So this is what we did in class, right? We did this and we did this. You can split those and then simplify each one by itself. So this 72 here, we can turn it into 2 numbers and multiply 72. And this m here, how do you get rid of this? How do you turn this into an exponent or get rid of the radical?
Oh, you take the index and the power.
So this will be what? 2 by 2?
Two equals 1. Okay. Because that's, trust me, I was so confused.
And then you simplify this. Whatever you get from here, you multiply them here, you get some a minus. Same thing here is going to be an m here and a b. And finally, you're going to end up, you can combine these two algebraic expressions here. So a, whatever a might be, minus b. And m, okay?
Okay.
Just split the radicals, simplify each one. Again, we use that rule in the class like this, p by n.
Yeah, okay.
All right.